Okay, so our project is about connecting clients and servers securely. So using RSA. So to start, how does a server and a client know that they are who they say they are, right? And how do they know that this information they're sending is secure? Well, one way to do it is for the client to have an ID card that it shows to the server. But there's a problem. If you have a public ID card on the internet, someone else can just copy paste that ID card and pretend to be you. So what we need to do is we need to have a public ID card or a public key and a private ID card or a private key. And you share your public key, which is saying I claim that I'm person X, and then someone else can use the public key to have you prove that you have the corresponding private key to prove that you are actually person X. Okay, so that's how this verification process works. So to do that, we're going to use RSA, and to use RSA, we need to generate primes. And so for for generating primes, we use this primality test, the Miller-Rabin primality test, which says that for each integer a modulo p, this claim is true. So essentially, if k is the order of a with odd part b, either a to the b is 1 or a to the 2tb is -1 mod p for some t uh, less than a. Yeah, where a is like the exponent of 2. Okay, so essentially what this is saying is that one of these things is equal to one of these things is equal. And so if this claim is false, that means that p is not a prime, right? So what we can do is for non-primes p, this is only true for 1/4 of all possible values of a, right? So we can essentially test all the value a bunch of values of a, say 100 tests, and if p turns out to be a composite number, we will get we the only chance that we would fail is there's a 1 in 4 to the 100 chance, which is very small, that we would falsely identify a composite number as a prime. Okay, so yeah. So this lets us generate very large primes, much larger than brute force, and we just randomly check numbers to do that. So now RSA encryption. So this uses the prime numbers that we just generated. So we compute n, which is the product of two random primes, and then the totient of n, which is p minus 1, q minus 1. So now we pick a public key a, which is just some exponent. Um, okay, yeah. And then we find the inverse of a, which is b, the inverse modulo phi of n. So that's the b such that ab has a remainder 1 when divided by phi of n. So that exists because we pick A to have a GCD1 with phi of n. Okay, so once we have that B, we can then encrypt and decrypt data. So you can see to encrypt data D, we compute D to the A and obtain a new thing D prime. D prime is the encrypted data. To decrypt D prime, we can compute D prime to the Bth power. And this works because if we encrypt and then decrypt, we would get D to the A to the B, which is D to the AB. But since AB is 1 mod phi of n, we can replace this exponent mod by 1, reducing by phi of n, modulo phi of n in the exponent, and then we would get d to the 1. So we get the data back. So encrypting, decrypting gives the data back, so this works. And the reason that this is secure is because you can't obtain the b by knowing a and n. You would have to know phi of n, which is n minus p minus q minus 1. And you can't know p and q unless you factor n, and that's impossible because n is very large, and it's very hard to factor large numbers like n. It's computationally infeasible. So because we don't know p and q, we can't get phi of n, and we can't do any of this. Okay. And then after we verify the client and server's identities, they can verify each other's identities. We need to establish a symmetric key for this single session use that we can use to encrypt all the data going between. So we will use AES to encrypt the data, but first we need to generate the key to encrypt that data. So to do this, we use a safe prime, which is of the form 2q plus 1 for another prime. And essentially the point of this is so that the multiplicative group modulo p has a size 2q, which means that essentially if you get some number g, as long as it doesn't have order 1 or 2, its exponents will be very varied and random, right? So g powers of g are very dispersed and random, and picking a safe prime lets us do that. Like dispersed and random modulo p. Okay, so then we pick a number a, and the server or our friend choose the number b. And what we're going to share publicly is p and g, and then I'm going to share g to the a with my friend, and my friend is going to share g to the b with me. Notice that we never actually share a and b themselves, just these numbers. And everything that we share is modulo p here. Then each of us can compute g to the ab modulo p since we have the missing piece. My friend sends me g to the a, I have b, I can compute g to the ab, and the other way around. We can both compute this, and now g to the ab is a random shared secret number that both me and my friend have. And even if a hacker listened to everything that we told each other, they still would not, and listen to our method, of course, they still would not be able to compute g to the ab because they can't determine a and b, since they would have g and a, g and g to the a, but it's very hard to determine a from that, since the discrete logarithm problem is very hard to solve. You're trying to find the logarithm base g of some number g to the a. and it's very hard to solve that computationally. So that's why you get a secure key that can be used for encryption decryption. Okay, so it's a messaging server, and and I'm running two clients connected to it, and they're all running on the same computer. But of course, this can be ran remotely. Okay, so our clients connected to the server, so you can see that they tested the identity using RSA, and then they use the Diffie Hellman key exchange here to get a shared secret key. So now it's going to start encrypting every message with AES, and it knows that the client is who it says it is, and the client knows that the server is who it says it is. Okay, so if we type help within the client, we can see all the commands. So another thing that we can do is type refresh other clients, and this will show us all the other clients connected. And I only have one other client here, which is this. And if I type it on this client, I would see a different port number than this because it's showing this client on that one. So it shows you all the other clients that are connected. And the main other command that we can do is broadcast. So we can send a message to every client. So hello, this is a cool new message. Okay, so they sent the message. So now we can do show messages. And you see we have all these older messages, but we also have the new message here. And so, yeah, so it sends the message across. We can do that again from this client one more time. Broadcast hi. And then if we do show messages, we can see that we now get a hi on this one. And the server is keeping track of all of this. Right here, it says it's sending the message hi, sending a message hello, this is a cool message. So yeah, this is how our encryption works.
Rundown of AES. So AES is basically just a symmetric block cipher. That's very common and standard in the industry. And since it's symmetric, you can just use it to encrypt in a forward pass and also use it to decrypt with the same key, which is quite useful. So this is a quick overview of AES, but before we get into that, let's look at how it works. So there's three types of AES that are popular. There's AES 128, 192, 256. That's just how many bits there are. So in this project, we're going to be using AES 128, which is basically just going to be using 16 bytes of input data. And 16 times 8 is just 128, which is where it gets it from. So we're going to be using this 16 bytes and turning them into this 4x4 matrix. And that's what we're going to be using later for our operations. So to get the key, first of all, we're gonna use the Diffie-Hellman that key from that exchange, and from that we're gonna apply the SHA-256 hash in order to just get our key. And we're gonna take the first 16 bytes to get that key. So we're gonna need to have multiple keys because AES 128 runs 10 rounds. So these are just like a bunch of operations is considered one round, and there's gonna be 10 rounds in total. And you're gonna need another additional key at the very start. So you're gonna need in total 11 rounds. Sorry, 11 round keys. So in order to make those 11 keys, you're going to have to do some key expansion. This is a diagram for AES 192, but it's a very similar concept for AES 128. So the goal is to, instead of every six, we're going to have to split these 16 bytes into four groups of 4 bytes. So let's just call each of those each of those groups a word, basically. And we're gonna try to make 44 of these because 4 times 11 is 44, so 11 key expansions. So in order to do that, we're gonna use this formula basically, where instead of 6, you can replace it with 4. For every multiple of 4, so your goal is to apply this XOR to the element that's the last multiple of 4, and you're gonna apply a function to the element right before that multiple of 4. Uh, in this case, the function is just going to be some rotation, some substitution, and also for every round, we're going to create a constant. It's just going to be powers of 2, like the first round is 2, second round is 4, and so forth. And for all other elements, we're just going to be XORing it with this, just the multiple of 4 that comes before with the element right before, right? Uh, so yeah, that's basically it for the key expansions. And just applying this formula gets you those 11 keys that you're going to be running every round. So now let's get into the rounds. So first off, you're going to be applying that first round key with the XOR on your cipher key to start it off. And then you're going to start these operations. So let's look at to that. So the first operation is subbytes or substituting bytes. And it's very straightforward. This is a standard substitution table based on the FPS 197. And it's just a simple lookup table where your corresponding byte goes to another byte and you just substitute that in. So that's very straightforward. And the next one is you're going to be shifting rows. So for the first row, you're not going to be doing any shifting. Second row, you shift by 1 to the left, and second row, third row, you shift by 2, and your fourth row, you shift by 3. That's also very straightforward. But then it gets a little bit complicated when you get to the mixing columns part, which is your third operation. So in this case, you have a matrix multiplication. This is the common matrix that you can be multiplying by on every column in your original matrix, right? So you can't just do straightforward matrix multiplication in this case. You're gonna have to do multiplication in the Galois field, which is basically you're gonna be converting all your binary into polynomials, and then you're gonna be doing multiplication on the polynomials, right? So in this case, 5 turns into 101, and that like bit just represents the coefficient of that degree in that polynomial. So in this case, x to the 0 has a coefficient of 1, x to the 1 has a coefficient of 0, x to the 2 has a coefficient of 1. So this polynomial is x squared plus 1. And we're just going to be multiplying the polynomials normally and making sure none of them have a coefficient of greater than 1, which in case you'll not use that. And you're going to reduce that by XORing it with this polynomial. Right? And after you're done with that, you're going to have to do a dot product for every row. And that's pretty straightforward because addition in the Galois field is just an XOR. So that's pretty straightforward. So we saw, and so at the end, you're going to have to do another round key with an XOR on that. So you're just going to have to keep applying these 4 operations 9 times actually, because on the last round, you don't have to do the mixed columns. But in total, you're using 11 round keys XORing that. But the problem is AES is only for 16 bytes. But what if you had text that was longer than 16 bytes? In this case, you're going to have to use CTR mode, which is basically converting that block cipher for AES into a stream cipher. So the goal here is basically just to input a 12-byte nonce with a counter. So the counter increases every time by 1. So that makes a 16 bytes in total every time. And that's what you're going to be feeding into the AES along with your key. And at the end, you're just going to be XORing that with your plain text. So you get a bunch of 16-byte ciphertexts, and you can just combine them at the end to get your final ciphertext if you require it to be greater than 16 bytes. And yeah, that's pretty much it. We also looked at string searching algorithms, which is quite useful for like malware detection and like big text. In our case, we used it as a control F for our messaging app. So naive substring search in a string is usually worst case O of n times m. So to speed that up, we looked at 2 different algorithms: the Boyer-Moore, which is for single patterns, and the Corasick algorithm, which is for multi-patterns. So the Boyer-Moore is worst case O of n times m as well, but in best case, it's O of n divided by m, where n is the length of the entire text and m is the length of the pattern. So the Boyer-Moore uses 2 heuristics. First is the bad character heuristic. So the goal of Boyer-Moore is to shift from the right to the left of the pattern. And as we do that, we have to check is if the character is matching or not, the last character. And if it's not, like in this case, there's a bad character, our goal is to keep a lookup table when we're pre-processing that tells us where the last character is, like the last instance of every character. In this case, it's A. So we now know we can shift by let's see, 1, 2. We can shift by 2. So that's what the bad character heuristic tells us. The good suffix heuristic is basically going to tell us if a bunch of characters at the end have matched with the text at this point. And if that's true, we're going to search for this exact suffix somewhere else previously in the text. And if it does have a previous instance, we're just going to shift the entire the pattern over based on where the suffix matches with. So yeah, you just take the max of the good suffix and the bad character. They both tell you how much you can shift your pattern by, and you just take the max at every step to match your pattern. The other one is a Corasick. So this is for multi-patterns, and best case it's O of n plus m plus k, where k is the amount of patterns you find. So it creates a tree, TRIE, where each edge basically in this graph is a character, and the nodes are just getting appended to these new characters. So if you do it like a BFS, you can construct this where you just propagate down one node at each step. And so this is a very efficient algorithm for multi-pattern searching. So we can do a broadcast like over here. I typed in hello world, my name is Rahul Dev. And then if we do search world, it shows up as the 5th index. Or we could do like search like hi, right? So it shows up in a previous message, so there's a THI here. And it also shows up in like hello world hi. And if you want to run a whole, that was for Boyer-Moore. And if you want to run a whole Corasick, you can search like multiple patterns like hi and then cool, right? And it shows you like the indices of each of them.